This project has been shared with you, so you don't need to recreate it, but let's go ahead and look at the results. So we did a time series simulation here so we can get the for every hour every day. And you see the size of the PV and storage that's being recommended. And then the outage, I asked XENDEE to actually find out when is the worst time to create an outage, and it said it's July 15th is the month with the highest average electrical demand, and then we're starting at 9 a.m. for 3 hours. So when we look at that time, so let's go to dispatch by end use. We bring in July, and we'll bring in day 15. You can see that we're running in an islanded operation from 9 to 11 a.m. With 9 a.m. we got the battery discharge and solar kind of carrying the load and EV charging and everything all on its own. So we want to make sure this actually is going to work from a physics perspective in power flow. So we're going to bring this into our power flow model and run a power flow analysis. So let's look at how we can perform a power flow study. And really the intent here is to make sure that there's adequate supply of electricity that can meet the needs of the load, and that we can get that electricity from where it's being generated to where it's being consumed in a safe and reliable manner. You're going to build the model you see here, and really the intent is threefold. One is to make sure that the size of equipment, and by that I mean your cables, your transformers, they're sized properly so they're not overloaded or underloaded. Maybe we can save money. So we don't want to have unnecessarily large equipment in the mix either. But then at the same time, we want to make sure under resilience conditions, voltages, voltage drops, system capacities are all good. And also, if we want to expand the system in the future, this especially comes into play if you're looking at community and campus microgrids, that we have a way to making sure that that infrastructure is being expanded. Again, everything is going to be safe and reliable in operation. So let's look at the buses that we're going to be defining for our power flow analysis. Again, we covered these in the earlier lesson, but we have this symbol, the grid power. This sometimes you'll also hear the term point of common coupling. It's essentially the slack bus that is the connection point of the microgrid to the utilities distribution grid. So it'll be a much higher voltage than what you would be using with your microgrid to supply your building loads. And then we have our distributed energy resources, your solar, your generators, and so forth. And then you have this other bus called a storage bus that can actually be both a load and a source, because if it's charging, it's a load, and if it's discharging, it's a source. And then we have the pure loads themselves. These would be our buildings, our EV charging stations, anything that really is consuming power that the microgrid is providing, or the utility and the microgrid together are providing. And then let's review the components that we're going to use to connect these buses together, and they're called branches. And these branches that we're going to be working with are the direct connectors, which really gives a lot of flexibility as you become more proficient in modeling. It allows you to connect a lot of different technologies directly with each other without any impedance in between. And then there's the cables. Usually these are underground. We need to define the size, the length, the ampacity, and then also their resistance and reactance values. And then for transformers, there's the bus, the size of these that connects two buses. And then transformers also, you can even define a cooling method. Sometimes they're air cooled, sometimes they're oil cooled, sometimes they're oil cooled with fans on them. And these are methods to increase the efficiency of the transformer so it can actually do more work. And then they also have tap settings, which are voltage control methods. They can move taps up and down, and this way they can control voltage, moving voltage up and down as necessary to maintain a certain voltage level at a bus beneath them. And these connect with the two buses, so they always have a from and a to location, if you recall, as you were building your one line before. But now we're just going to get into more details around the electrical characteristics of them. So with that said, let's jump right in and build the network that we're going to import our economic optimization and dispatch results into, and then we're going to make sure everything works together in a nice, reliable, safe way, both in a grid connected and an islanded emergency scenario. So the final step in building our one-line diagram is to introduce our distributed energy resources. Remember, this is a solar plus storage project, so we're going to put in a solar source and storage, and we're going to connect them to bus 3. That's going to act as our microgrid bus. And we're going to use a direct connector so there's no losses or impedance between these connections. And we bring in our storage as well. And for the solar, actually let's go ahead and change the name of the bus bar to microgrid bus. You don't have to do this, but I'm doing it just so you see. Now let's go ahead and edit the solar, and we'll put the array rating at 200 kilowatts, and we'll keep everything else the same. We'll keep the inverter rating the same, and we'll click save. And now for storage, again, all this input information we're actually putting in is going to get overwritten by the dispatch from the optimization. But for the inverter, let's put 300 kilowatts, and we'll put the inverter power factor at 96%, and we'll make the storage 1000 kilowatt hour as far as its capacity. And for the amount of energy already stored, you can put a number like 50%. I usually go with 80%. This way, if the battery needs to charge, there's enough room for it to do charging. And if it needs to discharge, it discharges. And typically with controllers, if you recall with the optimizer, you could actually set the minimum state of charge the battery should be in before it goes into an islanded condition. So that's really the process of building the one line. Yours should look similar to this. And the next step then is to bring in the dispatch and the optimization design information into this network, so then we can do a power flow study. So we do that by clicking on this option here, import economic results, and then click the plus button to create a new import. You should see your less than 7 project and then the results of the simulation, and then you'll see how the system is now matched the dispatch values and with the actual elements in your one line diagram. And it's already separated the EV load from the regular load. Now we get to choose what dispatch we want to bring in for what day, what month, and even what hour. Recall July 15th was our peak day, and we chose a 9 a.m. outage. So you can see from 9, 10, 11 a.m. The system's running fully islanded. So let's bring in hour 12, our noon hour, and we'll bring in hour 9, our fully islanded hour. So we do that by clicking on add, like I'm doing here, and we'll choose hour 9. So this way we can do a power flow simulation to make sure the system is able to operate reliably and safely when it's grid connected, and also we want to make sure it can do the same when it's islanded. So I'm just going to call this one peak normal and click save, and then click OK. And that's, you see, it brought both of those dispatch strategies in, operational strategies. We're going to go back. So that's the process of bringing in the optimization results. Okay, so now that we have the results that we want from the dispatch strategy and capacities from the optimizer, let's go ahead and choose Analyze, New Analysis. And we're going to do a power flow analysis here. So go ahead and click Next. And we're going to do a power flow analysis using the utility as a slack bus. It's our strongest connection. And we're going to choose that noon hour where we are grid tied. And I'm going to give the study name grid tied just so we know how to differentiate between the different studies we're going to run. And once we're happy, we're going to hit run analysis. It's going to do an error check for you. If there's any problems with anything, it'll point them out. But if you follow these steps, you shouldn't have any errors. You can download the results. You can look at the results graphically on the one line. You have some analysis result settings on the one line, so how you want the network colored for violations, so overvoltage, undervoltage, overloading, underloading. You kind of want to look for the greens, the oranges, and the reds. Those are opportunities to fine-tune the design for some savings or for some improvements in performance. As you can see here, you know, the voltage drops, you really don't want them to be more than 5% above or below voltage. And typically over voltage, you know, no more than 3%, under voltage, no more than 5%. And right here, we're rock solid. But you can also see that the battery is charging, so that dispatch and the charging logic has been brought in. So if we go back to that dispatch for that day, you see we have some utility power coming in. We have a lot of solar production happening. we have some EV charging going on, and the battery's charging. And you see all of this, and you see, your cables are loaded properly. You don't have any reds, which is great. You have some greens, which are some opportunities maybe for some cost savings. But when we look at some of this, also, even though something is normally colored, you might want to be thinking future as far as from a planning perspective. So this cable here, it's fairly loaded, which means if we do anything more or we want to add additional loads inside of our building, we might not be able to do that. So we have a few options here on how we can do this and look at the impact of it. One is you can just put in a bigger size cable. And there's some advantages, some disadvantages. The advantages, you got one piece of cable, one installation process, and you're good to go. The disadvantage is obviously it's going to weigh a lot more. It's going to be a lot bigger, which means it's going to require some additional labor, and it might not bend as easily. So if you're going to try to maneuver this, or you needed to make some bends, it's going to be hard. You can bring in the information about actually the cables and transformers to the network as I'm showing you here. So you can choose how much of the input data you want echoed back on the drawing. So here I'm just bringing in some for you. And you can see now, this is a 350 kc mil cable. And now let's go ahead and actually simulate this change. So we have made an infrastructure change. We've gone from 250 kc mil to 350 kc mil cable. Everything's the same. We're going to choose that noon dispatch and capacity design and strategy. I'm going to change the study name here to 350 just so we know. And we're going to run it again. And now let's see how much headroom we bought ourselves on that cable. And let's look at the drawing again, the one-line diagram with the results showing on it. And as you can see now, we're at 77%. So we have over 25, a little less than 25%, over 75% loading here. But what if we want to consider a different approach? The other approach is running smaller cables, but more of them in parallel. Again, this has the advantage that the handling and installation and the ability to manipulate and bend will be easier for you. And you can do that by changing the number of cables in parallel from 1 to 2. And let's go ahead and click OK. And you'll see now the ampacity has improved significantly, because now for every phase we're running 2 cables in parallel with each other. So instead of one big cable, we went with 2 smaller cables. And let's go ahead and do a new study there. You see how easily you can make these changes and see the impact it has from a planning perspective and operational efficiency on your distribution network. And you want to make sure, again, those voltage drops and the loadings are all within parameters. So here I'm going to make it 250 times 2. And let's run it. And boom, in a few seconds you have your results. Let's look at it now and let's see how much headroom we have. So in this situation, we have, close to 60% capacity left. So if there's any additional growth in, for example, the amount of electrical load that building is going to require, we have plenty of room. We don't need to dig the trenches and, install new cables and so forth. So that's the process of this. Now we're going to look at the islanded mode next.